Please welcome our team. Today we have a very interesting task where we need to develop a synthetic acid called alpha-5. Now, before we get started, it would be a good idea to take a look at the brief analysis of this field. This synthetic field is located onshore. It has a carbonate structure and comprises three layers, B1, B2 and B3, separated by shale breaks. Water-saturated layers are located both above and below the target layers, and this is a main complication that we will have to work on today. This field has been in development for 20 years. We need to develop it further over the course of 5 synthetic years. Every synthetic year is called shot. During every shot, we can perform a set of operations such as drilling injectors and producers. Both well types can be either vertical, slanted, or horizontal. Furthermore, we will perform selective isolations and apply hydraulic fracturing and acid stimulation. It is worth pointing out that due to a weak pressure support from the external reservoir boundary, a pressure support system has been implemented at this field. And although the accumulated void replacement ratio at this field is around 120%, which means the total amount of injected fluid exceeds production, the average reservoir pressure still remains quite low. That's why we need to look at how we can improve the pressure support system. All field operations will be carried out within the allocated budget. The budget of the first shot is $2.3 million. The more oil we extract from the field, the bigger the budget will be at the next shot. Therefore, we should find the most optimal way to organize budget. I suggest that we take a look at reserves analysis now. Let's start with the initial reserves. Now I would like to give the floor to the geologist and later to the petrophysicist.
The initial geological reserves of the field are estimated to be around 27.2 million cubic meters. The target oil recovery factor is 15%. As for now, we have already extracted 18% of these reserves, so there are still 8.5 million cubic meters left. This field has many challenges as it is divided into several structures by fault. There is a presence of uplift, and there are several structures in the south which are also separated by faults. The field have 3 layers. In the northern dome, all three layers are oil saturated. Between the domes, only B1 layer is productive. In the south, there are 2 productive layers, B1 and B2. Also, these layers have different permeability. Here is a map of average absolute permeability, and it is evident that in the north of the reservoir permeability is lower. Seismic section have been provided, therefore by analyzing this section, the cap of B1 was probably incorrectly determined along line 150. Most likely the cap result is differently. Our reinterpretation is shown in green. As I believe, the reservoir should lie higher, and therefore potential reserve could be hiding there. There is worth checking out, and it makes sense to drill new well in that zone. Therefore, the map of reserve roughly shows the area where we could be potential oil reserve, considering we perform reinterpretation of seismic data.
Does anyone have any questions about geology?
Can you please tell me how promising is the area southeast of wells 137 and 138?
There should be a promising reserve both in terms of seismic and sections. There may be uncovered reserve in the upper layer B1. It is quite likely that the reserve estimated here is true, so I believe that there may be potential oil in this zone.
Are there reserves in the area west of the well E3, which is bounded by faults? Is it worth drilling a well there?
Most likely, there may be reserve there. It is worth drilling between those two faults. Further on, E1 is closer. There the reserve is much lower. Here the level of the B1 reservoir still allows us to assume that there is oil there.
So we have three potential areas for drilling: in the north, around the well 138, and between the faults.
Yes, that's right.
How reliable is the reserves map at the drilling points of the zone to the right, located in the western part around wells 134, 135 and 136? Is there any clue if this dome stretches out further?
According to the seismic, after the fault, the formation becomes much lower. As we assume, it is most likely located below the oil-water contact.
In your opinion, which reservoir do you think is the most promising for further development?
Reservoir B1 in the south and perhaps reservoir B2 in the north.
If there are no more questions left, then I suggest that the petrophysicist will present an analysis of the core data and logging that we got from the previous team.
We're dealing with a deposit that is composed of organic limestones. The average porosity is about 15–16%, and the permeability is 50 millidarcy. The most promising wells are E1 and E4, where the cores were taken, and there is evidence that in the upper part of the formation B1, there is a layer with high permeability. In the well E4, the core data was analyzed. 3 zones with a permeability of less than 10 millidarcy, about 50–60 millidarcy, and a zone with an abnormal permeability, which is somewhere in the order of 300 to 500 millidarcy, are distinguished. Most likely, the upper part of the porosity permeability analysis points corresponds to the selected core in the upper layer B1. The permeability in the upper part of the formation is abnormally high compared to other intervals. Let's take well in the middle part of our field as an example. Here you can observe a misidentified oil-water contact on layers B1, B2, and B3. The oil-water contact is much lower, while on B3 it is much higher. I will also note that there is a presence of a small shale break with the overlying layer A. I would like to draw your attention to the fact that the B2 formation in the middle part of the field is interpreted incorrectly by B2. The gamma ray logging clearly shows the intervals, and they are so strong that they can be reperforated and used for production.
Are there still unrecorded reserves in the field?
This is only seen on the southern dome.
You also said about highly permeable layer. Is it found anywhere?
Yes, that's right.
The area around wells 110 and 111, where the unit B3 passes into the unit B1 from above. Does the unit B2 show any promises at this zone?
Reservoir B2 around well 110 is initially water-bearing.
We have now evaluated the initial reserves and information at the Alpha 5 field, and now I propose to evaluate the current state of reserves that we can identify by analyzing the production logging and well testing.
While studying this field, we observed many faults. According to log plots, we see that all the faults, however, are non-conducting, and basically, most of the wells have 3 layers, B1, B2, and B3. The skin factors in these wells have been analyzed and found out that many wells have high skin factors. Such cases include, for example, wells 134 and 138. They have a skin of about 20, which make them great candidates for stimulation. Also, according to the log plots, it's clear that we have autohydraulic fracturing on wells 101 and 102. So, it is necessary to take this problem into account during the development of this reservoir. According to the analysis of reservoir pressure, only 5 wells, namely 111, 113, 122, 126, and 129, are active in layer B1. The rest are already active in 2 formations or more. On average, the reservoir pressure is low, about 100 atmospheres. In the north, we see that the average reservoir pressure is 100 to 115 atmospheres. This suggests that it is necessary to raise the reservoir pressure to increase production. Some wells will need to be connected to the pressure support system. Also, high productivity coefficients are observed in some wells. This means that there are some thief zones where the injection could be going outside the reservoir. There are wells that have very low productivity. These wells should be considered for recompletion, put on injection, or stimulated to remove formation damage or the high skin. These wells include 104, 130, and 118. As mentioned above, all faults are sealing faults and non-conductive. Therefore, I recommend to develop this field on a closer spacing, provide effective pressure support, and remove formation damage.
Please remind me of the initial reservoir pressure at the deposit.
165 atmospheres. Since the previous team has already reduced pressure on this field, it is necessary to increase the pressure to increase production.
How do you recommend measuring reservoir pressure? Systematically?
I propose to take reference wells on each dome and spend 10 to 15% of the total budget.
You mentioned that some wells do not operate it on any specific formations. These are the estimates of the productivity of individual layers that differ in permeability.
For example, well 113 is only working in B1, and it has a high productivity coefficient of about 24. This means that it is in communication with other horizons above it or below it. This well should be surveyed to determine its actual production profile. Only then we'll be able to determine where the injection is going.
Let's refer back to zones 134, 135, 136. If you look at the model that was used during the well testing analysis, you can see that we used a model with infinite boundaries. That is, the boundaries in this case are not highlighted. How far is this area separated?
I will clarify it in the process and will make final conclusions.
I suggest that we move on to the results of the production logging analysis.
I have analyzed all the available past data from production logging and have identified 3 most distinctive situations. On the screen you can see production logging that was performed on injectors. I believe this explains why the reservoir pressure has dropped so much. Here are the production logging results for well 117. Formation B2 takes in very little, formation B1 takes a lot, and this usually happens in the formation roof where the main part of injected water enters the overlying water-bearing formation A. The situation is similar for wells 122, 132, and E3. The vast majority of the injected water from these injectors enter the overlying water-bearing formation that is leaking through the cement stone. In case of well 107, there is a cross flow, and the water flows through the top and the bottom. Therefore, if we perform remedial jobs to these 5 wells, and the ejection pressure will not increase above the point where it causes cement stone destruction, then the efficiency of the pressure support system will significantly increase, as all in the ejected water will flow into the target formations. The situation is similar with producer wells. Not all the water is coming from the reservoir. According to production logging at well 103, the majority of the water comes from the overlying formation A, where the reservoir pressure has probably increased due to the cross flows of the injector wells. The similar situation is observed in wells 108 and E4. There is a flow from the overlying water-bearing formation A and from the underlying water-bearing formation C. Therefore, if the remedial jobs are performed to these cross flows and the pressure is maintained below the point where it would cause cement-stone fracture, it is possible to significantly reduce the water cut and increase oil production. In addition to that, both production logging results show that roof of the formation B1 is operating at much higher level, which confirms the petrophysicist's conclusion that the permeability is much higher. Here, it is evident that the water that came through the reservoir also passes through this water-bearing sublayer B1. Perhaps it should also be isolated at certain wells after some point. It is possible to isolate this layer B1 at the injector wells, so that it is not longer injected into a highly conductive layer, as the water flows through it to the producer wells. In order for us to better understand what pressure should be maintained so that it will not cause a cement-stone fracture, I would also make a point-by-point test in the well that is about to be drilled, just to clarify what pressure we currently have in the overlying water-bearing formation, so that later in the resulting value is taken into the account when calculating the maximum allowable bottom hole pressure to prevent further behind casing circulations.
It's not production logging, is it? It is formation-oriented production logging.
Right. I have looked through the reservoir production profile, which was performed using a temperature logging suite and spectral noise logging.
Will it be possible to determine the effective reservoir capacity from the production logging? I think that this information will help to calculate the productivity of the well. Can you advise us how much budget should be allocated for production logging?
We need to survey the wells with a high water cut at least once to understand the location of possible crossflows, and then we can proceed accordingly.
Can you tell, are there any water shut-off work that can be performed on certain wells without prior production logging?
This is impossible to tell, as we do not know which interval is a good candidate.
Perhaps the size of the shale break between the target reservoir B1 and the water-bearing formation can tell us something. Is it possible to extrapolate these results after surveying one or two wells in the region?
If the cement quality was the same, then everything would be clear. There should be a cross-flow close to the water-bearing formation. I am not certain that they will have the same quality of the cement.
Now that we mentioned critical pressures to ensure there are no breakthroughs, I suggest that we give the floor to our technologist.
Good afternoon, team. As it was already mentioned, my task is to calculate the critical pressures and determine production targets. To find the minimum critical bottom hole pressure, I use this formula. P is the reservoir pressure on the adjacent water-bearing formation. PWF is our desired downhole pressure, and H is the distance between the perforated and non-perforated layers. Delta P is the average pressure variation at each meter. The final formula is shown here. Using this formula, we can calculate the downhole pressure.
Can you please tell us, to what extent can we stimulate the inflow in the producer wells and the injection in the injector wells? Or, in other words, which wells are you not certain about and can cause breakthrough?
I have analyzed the sections, namely open hole data, and concluded that in case of the producer wells, we have a minimum shale break of 5 meters, and based on the formula, we can lower the pressure at producer to a bare minimum of 45 atmospheres. And at injector wells, the bottom hole pressure currently can reach 228 atmospheres. Further, when performing perforation and isolation, these values may vary.
Do we have hydrostatic pressure in the water-bearing formation A, or is it necessary to confirm it?
I would advise that while drilling we call for hydrodynamic logging to help us find the reservoir pressure.
I want to give the floor to the simulation engineer who will be responsible for defining production targets for producers and injectors.
An analytical form was presented to help calculate the flow rates, where the input parameters include field summary and relative permeability. Next, we set the pump setting depth and top of perforation. Based on this data and the data acquired from production logging, the well testing determines the contribution of each unit to the total flow rate of this well. So, based on the total water cut of this well, we determined the production of each unit and also found out the water saturation for these units in such a way that the total water cut is mismatched, especially when trying to assess the potential. As previously mentioned, there is a minimum bottom hole pressure where there will be no channeling. Therefore, to calculate the flow rate for each well, first we require reservoir pressure and clear understanding of the current development and effective reservoir thickness. The model was adjusted with the latest production targets. Also, we need to account for reservoir pressure based on the results of the well testing and production logging. And we see that the wells where production logging was not performed are the primary candidates for further surveillance. For example, the well rates for well 126 didn't change even since we will provide a huge permeability value and a huge reservoir pressure value. The next example is the well E3. According to it, the injection rate is very high. The reservoir injection rate is even smaller than it was initially, according to the well testing. But still, the injection rate doesn't coincide with the actual rate. This indicates that this well has a target injection. Therefore, it is recommended that the part of the wells that had problems to be further investigated, so that we understand what is going on. We still need to evaluate the effectiveness of each workover in some way. As we remember, the injection started in the second year after development began, and we can see how this affected the liquid and oil decline rates. So, if within the first year liquid decline will be 30%, then by the fifth year, when the zone is covered by the injection, the liquid rate will be restored. If there was no injection at all, or the injection went to the other units, then it will continue to fall. The same thing applies to the oil rate. We can restore the oil rate to almost 100% of original by organizing the injection. Now, let's use all this information to evaluate the economic efficiency for each proposed workover. It is necessary to exclude wells where there was a channeling or production logging from our list.
There is a significant number of potential wells that require reservoir pressure measurement. Do we have to measure all of them at the same time? Or we can gradually measure the pressure over the course of a few shots.
The candidates were selected out of those wells that either didn't match the flow rate or the reservoir pressure was very different from the values of the previous well testing. I suggested taking a measurement where the formation pressure was not measured at all, and where it was measured you can leave it later for subsequent shots. I think that it will not be a bad idea to spend a part of our budget on measuring the reservoir pressure.
I have a question for a simulation engineer. Do you need information on the effective well thickness?
The entire calculation is based on the open hole data. Of course, it would be ideal if the results of the production logging will determine the effective reservoir thickness. This would make it possible to better predict the contribution of each of the unit and also choose the optimal production target.
The production logging specialist mentioned that the effective thickness in most wells correspond to the perforated thickness. Are there any discrepancies in your calculations?
There is a large uncertainty in terms of petrophysics, as there is an overlying unit B1, which is divided into two subunits, B21 and B22. That is, the top is very different from the entire underlying unit, 5-10 times. This unit makes a significant contribution to the flow rate of the well.
Will squeezing help at this conductive sublayer B11?
In my opinion, the subunit where most of the wells have high water cut and offset wells don't show channeling, I advise to isolate this subunit with subsequent opening of the underlying units B2 or B3.
Thank you very much. Then I'm giving the floor to the reservoir engineer.
Having reviewed all the data on the geological body structure, understanding the formation structure, their filtration and reservoir characteristics, by studying the well testing data, the current situation with reservoir pressure, effective thickness, dynamic model adjustment, understanding the minimum bottom hole pressures in producers and maximum pressures in injector wells, the following strategy is formed. I would like to recap our strategy starting with drilling. The main drilling strategy is to first start developing the undeveloped western slope of the northern dome by introducing new wells. On the screen, you can now see the estimated drilling points that I recommend performing to maximize the production. Here, you can see the horizontal wells S1 and S5 that will operate as producers, and assign S2, S4, and S6 as injector wells. Also, there is a promising rock pillar that was not covered by the development, which I propose to develop by drilling one producer well, S3, and one injector well, S7. After hearing the results of the analysis provided by the geologist, it is possible to redirect these drilling points to other zones, near well 138, or as it was suggested by simulation engineer, around well 134. We should vote for the final plan collectively. Due to the geological features, I still recommend replicating one-stage hydraulic fracturing in vertical wells and multi-stage hydraulic fracturing in horizontal wells. I would like to note that put hydrodynamic logging at a high priority during the development. Firstly, we should acquire an accurate reservoir pressure in our active aquifers A and C, and conducting hydrodynamic logging will provide us with an understanding of the reservoir pressure of our target formations B1, B2, and B3. We will be able to accurately determine the starting flow rate of newly drilled wells. Next, it is planned to conduct large-scale surveys of the field to remove any uncertainties and have full control over the development. As mentioned earlier, it is expected that at least 8 to 10% of the budget will be allocated to surveys. From my point of view, I suggest that for the most part we perform reservoir flow profiles, since they give more accurate results of the fluid movement behind the casing. The reservoir pressure should be measured at all zones. I advise carrying out as many surveys as we can, but we need at least 1 point for each zone. And for the southern dome, I suggest taking measurements at all 3 points, because it is very common. We must limit our budget. In the initial specifications, there were flow profiles for some wells. On the screen, there an example of well E4, which is a producer well. Let me elaborate. You can see the formation B3, which theoretically is also relatively complex, It has similar reservoir properties, but there is a large water inflow from the lower part of the formation, which, according to the aquifer operation, raises doubts that this is not the work of the formation of the sublayer B3. This is precisely due to the behind casing circulation from the aquifer C. Also, understanding that we have the work of the aquifer, even knowing that the formation B1 is highly permeable, we see a significant inflow of liquid from the upper perforation. It also raises some doubts, and I can assume that currently there is production coming not only from the sublayer B1, but also from the behind casing circulation from our aquifer A. In such wells as these, I propose to exclude performing additional production profile surveys and immediately proceed to workovers. On the screen, you can see a complete list of workovers that can be carried out based on the initial field information. The main activities involve developing non-drainable reserves at the formation B2, located in the southern dome. It is overlooked at many wells. I also propose to put into the development formation B3 at the northern entrance. I have many doubts about the current oil saturation. Most likely, the inflow there will be mostly water. Also, we already have some results on the behind casing circulation, and we can already conduct water-gas shutoffs on these wells. Furthermore, if we only consider producer wells, on the screen, you can currently see the specific activities for it. Well 132 is also very promising. It was transferred to pressure support system 6 months ago. Up to this point, it had a flow rate of 50 tons per day with low water cut. I propose to return this well back to production. It is estimated that if we successfully transfer this well to production and no complications will follow, it should return to the same production rate as it had before it was converted into an injector. Also, according to the results from the well testing specialist, there are wells with significant skin factor. I also suggest that we conduct stimulation on these wells by processing the bottom hole zone. The final priority settings will be made by the economist. Regarding the pressure support system, on the screen, you can see a list of those candidates that I propose as injectors. In addition to that, I would like to say that the injector wells also do not work at full capacity that have certain geological reserves. It is my assumption that they require perforation. My personal suggestion is to completely isolate the highly permeable layer B1 because there is a small layer B1 nearby and the shale break is small. I suggest to completely close the layer B1 to get the maximum economic benefit during this period and return to production from this layer after the reserves of the main layer B2 have been recovered. As I understand, layer B2 currently has the largest oil saturation.
How are you going to transform the well grid? By changing production targets? How will the resulting grid look like in your opinion? Is it optimal for this unit in particular?
On the southern dome, let's introduce a row-by-row water flood for wells 112 and 114 to create a row on the northern side. In the central zone, there is a well 122 out of 124. To support them, I advise transferring well 123. Further down, there is an injection well E3. It is proposed to support the injection of the offset well 129 here.
I have reviewed wells 134, 135, and 136 and they seem to penetrate both layers B1 and B2. However, they don't show any visible boundaries, which should be taken into consideration in the plans for pressure maintenance during field development.
That's exactly what I expected. At this section, there is a producer well 134, which produces a significant number of reserves. Also, since we will be transferring well 132 to producer, we should at least transfer well 136 into injector. I believe there is not enough candidates on the southern dome. We require additional injection points. Regarding the northern dome, as I understand, the zone around wells 110, 111, which works for the formation B1, is connected to the formation B3 of the main northern section. I suggest either transferring 111 into an injector or well 110 to compensate formation B2. We can also perform reservoir flow profile on inactive well 108. Based on the result platform relative workovers and transfer it into injection. Wells 101 and 102 are also promising, where according to the results of well testing, there is an auto-hydraulic fracturing. Let's run reservoir flow profiles on them. Perform workovers in order to close these fractures, reduce the injection volume, and carry out bottom hole treatment for the main target formations.
The well 108 is surrounded by a well 107 with an off-target injection. Maybe it can support the injection?
I agree. I suggest that after the results of the first shot, we should evaluate the work of the northern dome and enter additional injection points accordingly.
Do you plan to prioritize your survey list?
At the moment, I have specified only a draft list of priorities, which I believe are most promising. Of course, I saw the presentation of Reservoir Simulation Engineer, and this list can be further expanded and put in order of priority.
Do you suggest performing them right in the first shot?
I am afraid we don't have enough budget for that. Now, the economist will provide us with an accurate assessment concerning which wells we need to start with, because we will not be able to cover all the surveys in the first shot. So now let's prioritize each activity.
I would like to give the floor to the economist, who will show us the economic effect of various activities. This includes drilling new wells, workovers, and adjusting production target of producers and injectors.
Good afternoon, team. For an economic point of view, the main desired parameter is NPV, net present value. Discounting is the process of determining the present value of a payment or a stream of payments that is to be received in the future. Given the time value of money, a cash unit is worth more today than it would be worth tomorrow. The NPV formula is presented on the screen, where N and T are the number of time periods, CF is the cash flow, and R is the cost of capital. To calculate the NPV, we need to know the main cost items. The main cost items are shown on the screen. These are the costs of oil and liquid production, well servicing fees, the cost of workovers, as well as taxes. The discount rate is 14%. Now that we identified the main cost items, targeted workovers, and estimated their effects, we can start calculation procedure. To calculate the revenue, operating costs, capital costs, and tax costs, we can already calculate the NPV. To achieve the best NPV, it is necessary to determine the priorities of workovers. I would like to note that due to a limited budget, to obtain the maximum NPV, it is necessary to prioritize activities by PI, Profitability Index.
After we plan all the activities for the first shot, do we need to perform relative calculations?
Yes, it turns out that we will need workovers and expected effects that they will bring. Then it will be possible to make calculations and clearly project what are the values of NPV and PI for each workover.
If there are no further questions, we will assume that we have analyzed the current state of the deposit in the initial state of the deposit, and now we will start discussing the activities.